Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 33. It's on the magnetic field of a dipole. What is a magnetic dipole? Well, it could be a magnet. It has a clear north and it has a clear south. It could be the needle on a compass, or it even could be the Earth as a magnetic dipole. And so to understand how it works, we use an analog for that, an electric analog for that. So imagine if we had a loop, and that loop contains current, and it's just moving around in a circle. We'd have to hook it up to something. But let's say the current's moving in that direction. We learned in the last video that if you ever have current moving through a wire, we're going to create a magnetic field. And so let's use that right hand rule to figure out where the magnetic field is coming. So I'm going to grab that loop just virtually, and then I'm going to see that as I point my thumb in the direction of the current, then the magnetic field is going to come up right through the middle. And so that would be our magnetic field. Let's move the current. So let's move the loop a little bit. If I move my thumb now, it's pointing away from me. Where is that magnetic field coming? It's coming up right through the middle. And let's say I go all the way around to the back of that loop. I don't know if my hand could turn that direction, but we still have the magnetic field coming right up through the middle of that loop. And so this would be our magnetic dipole. It's going to be affected by magnetic fields, just like a magnet. So a good analog for a magnetic dipole is current moving around a wire, and so we're going to have a clear north and a clear south of this magnetic dipole. But any kind of a magnet is going to be a magnetic dipole. So like a compass needle, a floating compass needle is going to be a magnetic dipole. And so if we put a compass needle next to a magnet, again, that magnet is going to generate a magnetic field. And so that compass needle, since it's a magnetic dipole, is going to respond to that field. It's going to move. It's going to experience a torque and move in relation to that magnetic field. And we don't have to use a magnetic dipole. We could use iron filings, and if we put them out inside this magnetic field, they're both going to turn and respond to that magnetic field. And our Earth is also a magnetic dipole. And so other dipoles, like compasses, are clearly going to respond to that Earth. And so the first thing I want to make sure I mention is the difference between the dipoles we've talked about so far. So this would be an electric dipole. We have a positive charge. Remember, all the electric field lines would come out of it, and a negative charge, they'd all come into it. But if we move them next to each other, then we have this electric dipole. And you can see that those field lines, electric field lines, are identical to those of the magnetic field lines. In a magnetic dipole, we have a north and a south. And so we have the magnetic fields that are going to move around that. What's the difference between the two? Well, I can pull this positive off and the negative can stay there, and I've got two monopoles. But you never have a magnetic monopole. It doesn't exist in science. If you ever have north, then you're also going to have south. And so to understand how this works, we'll lots of times use this analog of current moving around a wire, and then we've got a magnetic dipole. That would be the M right here, and then this is going to be B, which is going to be the magnetic field. And so it's exactly the same as a compass. It has a clear north and it has a clear south. And so an example of a magnetic dipole could be a compass needle. And so let's say we have a compass needle, and then we apply a magnetic field coming from right to left. How is that magnetic dipole going to respond to that? Well, it's going to experience a torque, and it's going to move in that direction. Well, let's say we take a series of compasses and put them on a table around a magnet. They're not just going to keep pointing in the direction that they were. They're going to follow these magnetic fields of this magnetic dipole. It's kind of hard to visualize that, and so lots of times in a science lab what we'll do is put some paper over the top, and then we can sprinkle iron filings on it, and you can start to see those magnetic field lines. And you can see how this magnetic dipole, the compass needle, is lining up along those field lines. And the Earth, remember, is a magnetic dipole. It's filled with this hot fluid, charged fluid, and as it spins, it's creating a dynamo, and that's really creating a magnetic field. And so you can think of the Earth like a giant magnet. And the first thing you should see as you have this is it seems like the north is in the wrong direction. But remember, it's north on a compass needle that is pointed towards the north of our planet. And so that's technically the south end of the magnet, even though we refer to it as going north. And so if we were to take all of these compasses and put them on our planet and then instantly turn on the magnetic field, what are they going to do? They're all going to line up along those magnetic field lines. And so did you learn to describe the orientation of a magnetic dipole inside a magnetic field? Again, you just follow the field lines, and I hope that was helpful.